start second session now. Yeah, madam, can I start now? Am I audible, ma'am?
Yes, sir, you can start.
Okay, thank you very much. So, as I mentioned you that in the second session, we will introduce another case study that is also based on simple convolutional neural network, and the objective is to classify COVID, non-COVID images from chest X-rays. So I will again explain the network such that if anybody has any confusion, any doubt, still it can be revised or it can be cleared. So very simple network I have used there. You may change this network according to your requirement. You can keep on experimenting by adding more and more convolutional layer, max pooling layer. You can change activation functions in the different layers, and you can keep on experimenting. In that case, instead of using Kaggle or any other data set, we will use our own data from our local drive such that you can understand how you can address any problem whenever you are having some images. Even I received some emails you requested for that case. I think after completing this session, your confusions will be cleared. Even you can test using any other images or any other data after completing this session. So once again, we have some convolutional layer and pooling layers in these networks, and we have only one fully connected layer. And see, the big reason of choosing the simple network is nothing but to reduce computational cost, as I am running the codes here now. So if you wish, you can change architecture, you can change this architecture more complex such that your model perform better. Even whatever model we have designed, that is not sufficient to address this problem. You need to change a lot of modifications in the model architecture, as well as you need to use some regularizations, some tuning on these hyperparameters to achieve desired performance. However, if you wish, you can modify this code that I am going to present, and that will absolutely fine. So once again, input layer we are considering here, and the images we will consider is grayscale image, only one channel it will have. And if you notice, we have used a convolutional layer here, and number of filters we have used 16. The dimension of the filters is again 3 cross 3. So as number of filters, convolutional filter is 16. Number of channels in this activation map is 16. If you try to count this number of channels in this activation maps, there is some mismatches. You just extend these channels. For simplicity, I have not drawn much more channels here. Assume that there is 16 number of channels. And the dimension of this input is 64. The input we are considering is having any number of dimension. However, whenever we will train a model using the data, using those images, those dimensions will be modified according to requirement of our model. I will explain, I will show all those things. So in the second layer, you can consider here pooling layer, and it is not even mandatory. You may not use pooling layer here. You can use convolutional layer, again convolutional layer, again convolutional layer. So it does not matter. So and obviously if you use or if you change this architecture, there will be a different performance, and you can try in your own such that you can learn easily. So however, we have used pooling layer here. So the dimension, input dimension, special dimension was 64. So the pooling layer we are using of window 2x2 with stride 2. As a result, it is reducing to 32 cross 32. Means 50% samples will be reduced. After that, if you notice, number of channels will be present at this stage is equal to number of channels as inputs. So both are 16. So again, we have used another convolutional layer of 30 kernels of 3 cross 3. So as a result, 32, 30 number of channels in the activation map, and activation spatial dimension is also 32 cross 32. After that, again, sampling or pooling layer we have used using 2 cross 2 with stride 2, and the spatial dimension has been reduced by 50%. That is now 16 cross 16 and 30 number of channels. It will be exactly same to the input. And after this convolutional layers, we have used a fully connected layer that is of dimension 64. So according to your requirement, even I suggest you to increase this fully connected layers, and it may be here you can use 556 or 500, 600. After that you reduce to 128, and then you reduce to 2. So finally there will be a final layer, and that final layer there will be 2 neurons. One request from my side, if anybody is on unmute, please mute yourself. There is some noises. Kindly check whether you are on mute or not. I request you to mute yourself. Okay. So we are going to implement the simple CNN architecture, and objective is to classify COVID, non-COVID, X-ray images. And to do that, we need to have a lot of images of both classes, COVID, non-COVID. And some images are available on Kaggle. You can just Google and find out those images. However, I have collected some images, and if you see in this folder, we are here now. In this folder, we have a folder dataset, and please try to understand the structure of the data folders that we need to follow for this programming. That is very much important. So this is data set. It can have any name. According to the name, you need to use that in your programming. So in the data set, we have another folder, COVID, non-COVID. Even this name can be different. And see, in this folder, we are having 3 folders: test, train, validation. And if we export train, we are having again 2 folders: COVID, non-COVID. If we go to the COVID, you will have some images. These are the images we have kept there. And for simplicity, to reduce computational burden, only 100 images we have considered here. So some of the images are definitely I will show through my coding. The fact is, here we will have C number of folders: test, train, validation. Already I have explained what are the different purposes of using validation, test, train, saves. And each and every folder, we will have two subfolders. One is COVID, another one is non-COVID. And this COVID images, this is under test. There is only 10 images. Those are COVID affected. And there is another folder, non-COVID. These are normal. These chest X-rays are not affected by COVID. So that is very important. The name of the folders can be different, does not matter, but you need need to have this structure. It should be followed. Otherwise, you will find a lot of complexity to access the local drive. So this folder is in FDP underscore CEMK. I think you remember through CMD command prompt we browsed here, and after that we executed Jupyter Notebook command. So we are by default here. Here we are having data set, then COVID non-COVID, under COVID non-COVID, train test validation, and every folder will have COVID and non-COVID images. So in this way, even you can use, for example, you want to classify cat and dog. In this way, make your folder structures and keep images. For any other cases, if it is multi-class classification problem, for this case, it is two class, either COVID or non-COVID. If it is multi-class, you keep on increasing number of folders here. So Keras will automatically handle rest of the thing. So I think it is clear. Now we're coming back to the coding. So using those data set, we will train this model that already I have explained. And to start with that, the first task is to access local drive. And to do that, we need to have this OS, this reference that will allow us to access local drive from Anaconda from here. And we are importing this. Here we have defined a variable that is base directory, means from where train, trace, and validation dataset is started. Means under this folder, you will have train, test, validation folders. So we called as this base directory. So according to the names that you specified for your case, you need to modify this part. Even this name of this variable you can change. That does not matter. Later on you need to use that. Now, after importing OS and defining the base directory, Madam, can you mute every participant from your end? Hello, I am audible?
Yes, sir.
Yes. Once again, request from my side, if there is any participant or organizer is on unmute, please make yourself mute. Otherwise, there will be a problem. Okay, thank you very much. So after defining this base directory path, we want to see the images. how they looks like, nothing else. And this portion is absolutely optional. Means if you don't want to visualize those images, if you don't want to see how those images looks like, that does not matter. You still can have AI model, a DL model, and you can able to train that model, and even you can use according to your requirement. So although this is optional, but I suggest you always look for that. So if we execute this, I think you remember this portion. These are the plotting related matters. And to show this plot through graphs, so we need to use these libraries. And this code is nothing but in matplotlib, to show a plot or image, we need to use show command. So if you don't want to use that command, you place this magic function. These are known as magic function at the beginning. So without using those show command or function, you will still able to show the images. After that, number of rows and columns that I have defined, that is nothing but total 16 number of images I want to show from the training data set. And to show them, we are creating a placeholder for a graph 4x4. And indexing means, I think all of you ever with MATLAB plots. So to access particular subplot, we need to have some index. It will start from 0 to 15. And that's why we have used this. Here, as we wish to show training data, so we are defining the path where the training COVID images are located. So we are joining using this function OS that is present in OS join, and basically another path that has been created here, and that path is indicating where COVID images are located. So before that, I need to execute this block. Now, in this path, we are having the training images, those are affected by COVID-19. This is another option. Here, this is commented. So if you wish to access that folder directly, does not matter. You use this code, then you comment this line. And this, as already I have defined base directory, so that's why I have used this. So whichever you want, you can do that, no problem. After that, to access particular images, we need to have their name. And to get their name, we need to create a list here. And to do that, we have do this. So this is basically a frame or list simple, where the name of the images will be kept on. So I also printed this value such that you can understand very easily. Sorry, I think there is some name OS is not defined. Sorry, I forget to execute this block. Okay, so now see, this is one image where that is present under COVID-19, that is under train folder. So if you see under train COVID, non-COVID, train COVID-19, this is COVID.0.jpg. So this is COVID.0.jpg. Means from this folder, we are just accessing first 8 images, file names, name of the images, nothing else. So these are the names of the images. Now these images we want to show, and to show that we are executing this block. So I think from my side I will able to complete this session within maximum 310. So if you have any questions, kindly note down. I will answer all the questions. It does not matter. Okay. So here you can see those 8 images. These 8 images, those are coming from train folder. And if you notice, the dimension of the images are not same. But at the first step, whatever data set we have used, that was only for handwritten, and all images are same size. But here images are of different size. Even in fact, in practical use cases, this is the case where you don't expect images of same size. So these are the images. Now, if you want to show some non-COVID images, for that also I have written the same codes, same like, only I have changed the path here. Instead of COVID-19, it is non-COVID. And again the same, if you visualize them by executing this block, yeah, these are the normal images. So this is basically what we have done. We have just visualized the images, how they look like, and we have imported the data set, nothing else. Now we need to start modeling, and before modeling, as already you aware that there is a portion or very important phase, that is data processing. So data processing we need to have now, and in the data processing phase, I think all of you understood that there is one compulsory requirement. We have to make all the images in a same size, and according to our model, as we have defined 16 cross 16 for these images, so it should be not 16 cross 16 we have decided here. So basically I will show you how the size of these images, if we consider 16 cross 16, here also how we are getting 64 cross 64. So according to your model, what is the dimension that your model expect, you need to make that dimension for all the images. And to do that, we have this function image data generator here, that is the class where it resides. It resides keras.preprocessing.image. So from there, we are importing this class, and this class will also provide you various kind of preprocessing operational supports, like you can augment, you can share, means you can say you can change the phases of the images, rescale, resampling, everything. Keras has provided that class file to do that. So we want to go for mass processing portion, but one important thing is we need to resize the images into 64 cross 64. Another one is, as already I mentioned, and this first up, our model should be provided the data or values of tensors, those are having 0 to 1 values. So that's why normalization is another important portion or task. So to normalize this, we have used this. This is a variable, exactly we need to use this. Then 1 by 255, the maximum value of the sample. For 8-bit image is 255, like the previous session. Again, we have divided for all element. So it is now 0 to 1. After that, what we will do, this is basically an object initialization. And that object is primarily taking a value parameter that is whatever it will get, that will be rescaled by this. And this is a variable or reference variable referring this object's instance. Now we need to call another function that is so from directory and will be invoked on this reference variable train data gen. And as this is variable, it can have any name. Now whenever you execute this function, it will just allow you to show the images from this directory train. And after that, see, in the same function, we are having another parameter, target size. Again, this you can't modify this. These are system defined until and unless. Sorry. If you modify these variables values, then you will get error. So to modify the size of the images, there is target size, means whatever image will be flowed from this directory, that will be converted into 64 cross 64. And once again we are having batch size here, how many images you can consider at a time. It can be 10, 100, 20, 5, even 1 also. Even you can omit this portion, means this parameter. By default, it will take 1. Then class mode, as we are going to address a binary class classification problem. So that's why it is important to mention binary class mode. If it is multi-mode, then also you need to change this value accordingly. By this, Keras will understand that whether he will perform one hot encoding or any other one encoding, means the category of the label will be performed after mentioning this value. Similarly, we have processed other images. Those are in the validation and test folder. Exactly, they all codes are same. Only the dash size is different. For validation and test, they are 5 and 5. So if we execute this code, see, after execution, we can see here, once again, the backend is TensorFlow. That is mentioned here. And if you see how many images that resides in different classes, different folder, that has been mentioned there. So it does not matter if there is any imbalances in between number of images. For example, we are having 100 COVID images, but we are having only 150 COVID images in the training folder, then it will be 250. So there will be no problem. And as in this training folder, there is 2 subfolders. So that's why Keras considers this 2 subfolder as 2 different class. So similarly, for other folders also the same. So the data processing portion is basically over. We mainly resized our images to 64 cross 64, and we normalized the values of the grayscale values of the images. Nothing else we have done here. Now it's time to model, to define model, and then train, execute, evaluate everything. So in this modeling, DI modeling, our first task is to import the necessary libraries to define, train the model. So once again, these are same. So we have imported sequential, we have imported Cont2D. If you notice, in the previous example, we have used comma, Cont2D, comma max pooling. So in the both way, you can import them individually or you can import them through comma, because they all are coming from the keras.layers. So as you wish, you can go ahead like that. So whatever required tools to work with model has been imported here. Now we are defining our CNN. So this is exactly same whatever we have defined in this diagram. So there in the first convolutional layer we have used 16 filters. After that subsampling. After that another convolutional layer we have used 30. And all the windows for convolutional layer is 3 cross 3, or for pooling layer it was 2 cross 2. So if you see, after considering this reference, that is referring to the object of sequential class, and this time I am giving the name of the reference is my CNN model. Now we are adding those layers one after another. So again, this is same 16 number of filters we are using. Dimension of each filters is 3 cross 3. Yeah, is there any question?
No, it's no answer.
Okay, no problem. So 16 number of kernels we have used and their dimension, spatial dimension, and this is input shape. Earlier we have used a different variable to define that. So this time we are directly using here. If you see the input shape, sorry, I mentioned you that input size is 1, basically 3. Sorry, number of channels per input image is 3. Although those are grayscale, but there is 3 channels. So that's why it is 3 now. And after that, I mentioned that you need to specify activation function that will be used. Here we have used ReLU like the previous one. This is the new thing here. In the previous use case, we have not used this. The same padding means, if you notice this diagram, the size of the input is 60 cross 60, sorry, 64 cross 64 cross 3. And see, after having this convolutional layer, we are having 16 number of channels of the activations map due to these 16 kernels. But what is the spatial dimension? That is 64 cross 64. And this time, this is exactly equal to the input one. Means I am considering the size, spatial size of the input images as 64 cross 64, and the corresponding output having also the same spatial dimension. Even if you consider this layer here, Here the dimension, special dimension is 32 cross 32. Here this is 32 cross 32. But for earlier problem, if you see here, those dimensions have been reduced. It was 32 cross 32. It has been reduced 28 cross 28. Means whatever the size of special dimension, here we want to keep that. And to do that, we need to pad some zeros around the input images. And to mention that, we have this parameter padding. We have this parameter padding. So if you don't mention this parameter, by default, your model will consider it as there is no padding. If you mention this value as same, means I am expecting the same dimension of the output as input. So that's why it is important here, if you want to have the spatial dimension same as your inputs. And rest of the parts are same, exactly like the previous one. You can have multiple number of convolutional layer, pooling layer, either alternatively or consecutively as you wish. So Keras will handle everything, the size of tensors, everything. Only you need to mention the input carefully. And after this convolution portion is over, once again, we will have flatten layer, because we have defined these portions. Now we are moving to this fully connected layer. And to move this fully connected layer, we need to convert this multidimensional activation map into one-dimensional vector. To do that, again, we have used flatten layer like the previous one. So this is just converting this output after this into one-dimensional vector. After that, we have used a dense layer, fully connected layer, having 64 number of neurons or inputs. See, here we are having 64 number of neurons. Now, in the final stage, as we are expecting here whether the input image is at the final stage, final layer, we are just expecting whether input X-ray is COVID affected or not. Means we want answer in terms of yes or no. Suppose if you want some value with probability, then it should be 2. Nothing else. So to simplify our things, we have considered this. So I think this portion is very much clear to you. There is no confusion. So we have defined our model. Now it's time to see our model architecture, how whether we have defined everything, those are correct or not. So this is first convolutional layer. After performing this convolutional layer operation, this is the shape of the activation map. 16 number of channels, 64 plus 64 spatial dimension. This is learnable parameter. I already told you how to calculate this learnable parameters. Again, for pooling layer, there will be no learnable parameter. The pooling layer we have used 2 plus 2 window is tried 2. By default, it is 2. If you use 2 plus 2 window, and after that, the number of channels are same, but this spatial dimension has been reduced by 50%. Then again, we have used convolutional layer. This is the total number of learnable parameters for this convolutional layer. Max pooling, then flatten layer, as this is just converting the dimension of the multidimensional array to one-dimensional. There is nothing to learn. There is no learnable parameter. And finally, we are having two dense layer, this one and this one, and for that we are having this learnable parameters and 64 numbers of neurons before the final layer, and the final layer we are having one neurons. This is the total learnable parameters that is defined by model. Sorry, is anybody asking any question?
No,
Okay. Okay, so we have defined our model, we have checked the model summary. Now it's time to compile. During compilation, optimizer, what optimizer will be used, that you need to mention, what loss function and accuracy like the previous one. Now it's time to train our network. So it is started to train. So if you notice this, so we are using this training set that was processed. This is the training set. During data processing portion, we have processed the data and we have used this reference variable to refer to the data. And after that, we have used a number of epochs, and that is steps per epoch. If you notice, there is two epochs. This is epochs over epoch. Means total, this is 10 number of epochs will be considered. And each and every epoch, there will be 40 number of iterations. And to validate our model during training, means to test our model during training, we are using valid set. That is also preprocessed and referred here. And this is validation steps. So during 20 times for each epoch, it will be iterated. And for training one, it is 40 times it will be iterated. So I suggest you, for your cases, you increase the values. It may be more than 100, even epochs may be more than 500, like this. If you notice, the accuracy that already has been achieved 100%. Now, is it really possible by using this very less number of images, by using this very simple CNN to achieve 100% accuracy? So it is question from my side. So after explaining these portions, I'll try to have that answer from your side. Even I will explain what will be the actual answer. However, training has been done. So now we are saving our trained model for later use. To do that, we are executing this. The model is already saved. And if you see, there is two things. One JSON file we have stored, another one is .h5, HDF5. So basically, this file will have learned parameters, that is values of weights and biases. And the JSON file will have the architecture of the CNN model. So to use them later on, you need to keep both of them. So now it's time to visualize our model performance and evaluate our models, how we trained our model and how it is performing. Once again, to understand or to have this name exactly, we have executed this. This is optional. This is not required here. Now, yeah, if you execute this block of code, that is exactly same like the previous one. Nothing has been changed here. So you will see for 10 epochs how our model has performed during training. Means how our model is learning. So this is accuracy plot, this is loss plot. So as expected, both for train, sorry, this will be test. I think you should modify this value here. So instead of test, you write here validation. Otherwise, you will be confused. So I am. This is validation. Okay. So this violet color or blue color is for train and this orange color is for validation. So as expected, with the increasing of number of epochs, both accuracy is increasing for both the training as well as validation. And for loss, it is reducing with the epochs. So now we are testing the model. This is the test score. We have used the test images to test our model. If you see, this is very interesting. The test accuracy is 94% and error about 95%. However, loss is near about 60%. So something goes wrong there. So definitely I will explain. However, in this way, you can see the performance of your model using your test data. Now, if you want to visualize those layers, means I have mentioned several times this convolutional layer, and after performing this convolution operations, we are having this activations map. So how they looks like if you want to see them. For that, here we have two blocks of code. If you execute them, you will able to see the filters and activations map. And to do that, we need to import this model because that already trained model already saved in the local disk under the results my CNN model JSON, uh, like the previous one we have seen. I think there is a result. Yeah, my CNN model JSON and H5. So this model we will use to visualize convolutional as well as activations map layers. So that's why we need to import this model from JSON that will help us to convert JSON file into the CNN architecture like file.